All right, had a bunch of people come in this morning for help on homework 2 and the ODP, and mostly got people squared away. So, um, hope everyone had success with that. Any remaining questions? So let me just show you a solution to ODP 407. And I'm not giving you a new ODP today, so we'll take a break and let you finish programming assignment 1. So here's a solution for the ODP. So right, print a prompt, get an input from the user, which I called num, and then here's how we have to write our conditionals, right? So the square brackets and the spaces and all that. And since I wanted to test 2 things, double ampersands in between, lots of spaces around everything, right? So if the number is greater than or equal to 1 and less than a number of 3, in other words, if it's a legal number, what do? Echo OK and exit, right? So that part's the easier of the tasks. But if this condition is not true, it means they typed in something illegal. So now I have to do the second part of the problem, which is print out the word ERR, print a prompt again, get another number from them, the exact same if statement, see if the number is legal. And if it's legal, again, I'm going to say okay, and I'm going to exit, same thing I did up here. But this time, if it's not legal, then I'm going to say fail, and the program ends. I just exit the script at that point.
Is this a finished code? Like it's legit code?
Yeah, this will totally do ODP 407.
Oh, okay. So why is there no quotes around echo for like okay and error?
I should have put quotes in there, but I was being sloppy. So the actual reason is, if you echo something like, a bunch of characters, it'll just echo it. You don't need it in quotes. But suppose I wanted to, say, I like money, right? It's not going to show $money because the $, it interprets that as saying, oh, money must be a variable, show me the value of that variable, right? And so in this case, I would put the whole thing inside single quotes and suppress the evaluation of that $. Or echo.
So if you use double quotes, it'll still do the same as not doing it. So
Correct.
single quotes is what takes that away. Okay.
Yeah, so here's a better example. If it's like, this is good, right? Oh, that actually worked. Right? So if I say echo star star star, it gives me something unexpected, right? It gave me a bunch of file names, right? If I really wanted it to say star star star, I should put that inside quotation marks. So there are a few special characters that are interpreted in special ways, and if we don't want that weird interpretation to go on, go ahead and use double quotes around it. All right.
Okay. Okay.
And I'm trying to be better this quarter about, like, in all my examples doing that, but this is code I wrote before, so I got sloppy. Let's see. My if statements use parentheses. Is this not good practice? You will not get points if your if statements don't look like this. If you use parentheses in your ifs, you'll get 0 points for that. Right? So this was the whole point of that bash how-to handout. And it says in the very beginning, you've got to do it this way and this way only. So that's my sort of one claim to dogma in this course is bash if statements, conditionals, and arithmetic expressions have to be done the way they're described in that handout. So if you already...
Can I ask?
Yeah.
Why would you put it in parentheses? Is there a special time for that? Because I feel like how we have it here is easier because you're not having to shift, and use a special function. Like you have to use shift 9 to get parentheses, or you could just use the. Yep. you know, open interval like that.
So if you use parentheses, it looks more like C code, right? And most of us, or most people who are using Bash, are coming from a C background, and this is kind of bizarre looking, right? And it's really picky about spaces, and when you use parentheses, it's not as picky, right? And so it almost makes more sense to use parentheses. But when I decided to teach this stuff, I tried to find something that would be consistent, something that I could use, you know, one style that would work for whiles and work for ifs, and that was what I converged on, was using the double brackets. The other thing with parentheses is, because it looks like C, it's really easy to do things that make sense in C but don't make sense in Bash. And so I wanted to present the way to do this in Bash as something that would be, you know, as separate as possible from how we do it in C, basically. I think that was my motivation.
That makes sense. Yeah.
All right, go ahead and send me an attendance note. Let me know you're here. And any other questions? All right, so let's look at some of the logic in PA1 related to this business of whose turn it is. And this is the other piece that can trip people up sometimes, is depending on who starts the game, right? You might have one of two situations going on. So if the user goes first, what does your basic gameplay look like? Oh, let's see, question. Yeah, I can miss questions in attendance pings. Okay, that's all we got. Using this when you mean less than or equal is generally a mistake. It might end up working, but don't do that in a conditional statement. If you want to see if something is less than or equal to, always use -LE. If you want to know if something is greater than, always use -GT. Sometimes that'll just give you outright errors. Sometimes it will work, but silently do something different from what you want. And sometimes it'll work and it'll look like it's doing the right thing. But that's not proper syntax for a conditional, the way that we're writing them. So yeah, I would rather you do them, but it's actually stronger than just my preference. Why does Bash not play well? Well, less than signs and greater than signs have special meaning to Bash. We're going to talk about those today. They have to do with something called input and output redirection. And so that's the first reason. And if you can't use less than signs, then having a less than or equal doesn't make as much sense. All right, so suppose the user wants to go first in your program. So you've gotten the number of sticks, you said who goes first, and the person typed a lowercase u, so it's going to be the user going first. So what does your basic game look like? Basically, you have the user take a turn, and then you have the CPU take a turn. And then you go back up to the top. And if the computer is going to go first, then it looks almost the same, but you know, obviously the computer goes first, and then the user goes first, and then you go back up to the top. So it's potentially tricky trying to write one bash script that can do either of these things, right? Because here we've got the user going first at the top of this loop, and here we've got the computer going first at the top of this loop. So how do we reconcile these? How do we make one bash script that can do either of those? And there's two approaches. let me talk about both of them. The first one is generally useful. And this is something called stateful programming. So you've heard me talk about this a little in Engineering 270. The idea is let's write a single loop that will do this or that based on the value of a variable. And this variable would be set, you know, when the user says U or C for who should go first. And based on the value of that variable, we'll end up doing either this thing or that thing. So how could we do this? So let me put a note here. Turn is set to U for a user turn and C for the computer's turn. So this is a state variable. This is like a flip-flop in Engineering 250. If it's the user's turn to make a move, we're going to set this variable to a letter U. If it's the computer's turn, we're going to set it to a C. I could set it to 1 or 2. I could set it to A or B. I could set it to user or computer, right? But it's a flag. It's something that's telling me whose turn it is. And if I have this variable, I can make a loop that looks something like this. I can make an if statement which says, is the turn equal to U? And if it is, then I'm going to say, do the user turn. Get the number stick, show the pile, see if someone won, etc., etc. And when I'm done, I'm going to change this state variable to a C. And I'm going to go back up here to the top. If turn is not equal to U, I'm going to assume it's the computer's turn. So I'm going to say, do the CPU turn. And then I'm going to set this variable to U. And I'm going to go back up to the top.
Do you think that having a string value as opposed to a number value would be better for like making sure that everything is incremented properly, just in case, or?
It's totally up to you. So you could switch between 1 and -1, right? And that's totally fine. You could switch between 0 and 1. The only thing to sort of keep in mind is if you're debugging this. Well, when you're writing it, you know, is it more or less likely to make a mistake doing one thing or another? And that's very personal. That's up to you. And when you're debugging it, if you're going to print out, you know, what the turn variable is equal to, are you going to have more or less success if you're printing out, you know, a 1 and a 0, or a U or in C, or a, you know, something longer than that, and so on. So it's totally up to you. Since this is your code and you're the one writing it. And so on. Now, if you were working on a group project with other people, you would probably make some decisions as a group and say, you know, okay, so here's what our state variables are going to be, and so on and so forth.
Okay, so there's probably very low, if you're incrementing up and down by one number, there's probably low chance of it actually making a mistake or something.
Yeah,
Just
yeah.
like do a unit. Okay.
Mm-hmm. All right, so string concatenation in bash is there's not really a concatenate operator, but we can kind of do something like that. So x equals hello. If I wanted to add, you know, the word there to this, I could say x equals $, $. Well, let's add 1, 2, 3 to the end of it. No, well, okay. Really, I would just say $hello, and then I could add the word there. And now if I echo $x, oh, let me restart that. Okay, x equals hello. Okay, now if I said x equal to $x followed by there. Now if I look at the value of x, it's the old value, hello, with this new thing appended to it. So I've done a string concatenation, but not really. All I did was say, take the current value of x and take the word there, and those two things side by side, let's store that in the variable x. But it gets a little tricky because if I wanted to you know, add this without a space, it's not going to work because Bash doesn't know that what I mean is I want to take the value of x and then add THERE to it. It thinks x there is a variable, and I want to just see the value of this variable called x there. So that gets a little weird. So using spaces makes it easy, or I can like throw my x inside curly brackets to say, hey, this is a variable named x, and this is not part of the variable name. And so if I do it like that, that'll work correctly. If you want to print a $, you can use single quotes. So if I echo single quote $x, it'll just show me $x. If I do a double quote $x, it will evaluate x and show me the value of that. So that's similar to C.
Now I got a question.
Yeah.
If you wanted to print out a value but also have a $sign, so say you want to do like $5, right, or something like that, but the value is a variable, could you do single quotes around just the like $sign?
Yeah, so echo $x, and then I could follow that with you know, a single quote $sign, and so that prints $5. I think I can leave the space off. So like that. Dealing with quotation marks in Bash always gets a little confusing, and sometimes you'll stumble into a piece of code where there's like, you know, 12 single quotation marks and then 10 quotation marks and something else, and it gets weird. It's one of the odder aspects of a lot of scripting languages, but Bash too. But yeah, that's a way to do it.
So in this statement you have here on 5019, could you put that $sign with single quotes in before the $x there, and
Yeah.
that still work?
Sure.
And that would put the $sign in front of the 5?
That should work fine.
Okay.
And let's just be extra super duper weird about it. That does not work.
Okay, so that doesn't work.
Yeah, so a single quote inside double quotes just prints as a single quote.
That's interesting.
Yeah. All right, how do you loop back?
Something like that, you'd want to like double quote, do a statement, then put your single quote there, and then another double quote.
Yeah, yeah.
Okay.
Yep, exactly.
Okay, yeah, that makes sense.
Yeah. That's never something to do late at night when you're tired, because you can just lose yourself for like days in a big rabbit hole of quotation mark based pain and misery.
You mean like having an extra 10 lines above your code?
Yeah, for example. Okay, someone said, how do you loop back to the beginning? So you could do a while loop, right? So if I wanted to play this forever, I could say something like while 1 equals 1. And that's a nice forever loop, right? So while space bracket bracket space 1 space dash EQ space 1 space bracket bracket do, and then I could put all of this inside and put it done at the bottom. You can do other versions of loops, but that's our basic way to go back and repeat code in Bash or most, you know, structured languages is to use a loop, and so a while loop would look. Or you could do while sticks left is greater than or equal to 0. That would be a better way to loop forever, because then when the number of sticks gets down to 0, you would exit the while loop, and then you could put, you know, the closing statements at the end of your script. All right, so this is one way to manage both of these these situations based on the value of a variable. And what we're doing is we're making a single loop, and each time through we'll either do the computer's move or the user's move. So if the user's going first time through we'll do the user turn. Next time through, turn will have been changed to C, we'll do the computer turn and change this to U. Next time through we'll do the user turn. Next time through we'll do the computer turn, and so on. And like I say, this is a really good general purpose concept, using a state variable to control what our same set of code does, right, depending on the value of this variable. There's a different way that we could manage this, and this is a little more particular to this assignment. But here's another approach. So we could do something like this. Do a conditional which says, should the user go first? And if yes, go ahead and do the user turn. And if not, just come down here. And now let's just make a loop. CPU turn, user turn, and let's go back to here. Alright, so what have we done? We're basically just coding up this version of the loop, but if the user wants to go first, we just have a special section of code in the very beginning before we loop, which says, hey, it's the user who wants to go first, let's do the user turn once. And then we go into this loop which does CPU user, CPU user, CPU user, and so on. So that's another option. So whatever works, right, for you, and this is part of the stylistic aspect, the creative aspect of coding, right? Even at the algorithmic level, we can come up with totally different approaches to accomplish the same thing. And unless you're given a specific algorithm, like, you know, how many sticks to pick, it's really up to you. And I want you to, you know, if you haven't already done this, I want you to feel very sort of free to explore the creative space that you're working in, and find what your style is, right? And it will change over time, and it will be different from mine, it will be different from somebody else's. But I don't want you to get bogged down thinking like, what is the right way to do this? Okay? Other than the details that are in the assignment, the right way is the way that works and makes sense to you. Right? So should you do something like this? Should you do something with a state variable? It's up to you, right? And this will come up again and again and again. And the closer you can be working to something that, you know, sort of matches your natural style, your way of thinking, your experience, and so on and so forth, right? The more success and, frankly, the more fun you'll have doing your coding. So yeah, feel free to explore. All right.
So if we don't need to put anything in there, like say we're down to 2 sticks, and the person who's turned it in says, "Oh, I want to take 3."
You don't have to worry about that. So if they only take 1 stick, right, they only took 1 stick. But if they try to take more than what's left, don't worry about it. I mean, they took the last stick, they won.
Okay.
And when I test your code, I'll show you more or less exactly how I'm going to test your code. All right, so first of all, I'm going to look for, I'm going to download your repository, which is CSE224. and I'm going to say change my directory to PA1. So you definitely want a directory underneath here called uppercase PA1. And if I can't do that, or it doesn't find it right, there's a point deduction for that. So I'm going to go into PA1, and then I'm going to say stick. So inside here, you want a file called stick with the executable bit set, you know, and so on and so forth. So, so what will I do? I'll go into PA1, and I'll say stick. And it should say something like this, right? Ask me for how many sticks. And I'll, you know, put in a number of sticks, and I'll say user should go first, and I'll play the game, right? So I'll put in some random numbers, and what I'm hoping to see is that, you know, after each person has made a turn, the number of sticks has gone down. There's a picture showing the number of sticks with a number in parentheses afterwards. The computer is picking sticks, and at the end, you know, the computer wins. I don't care if you show me the remaining pile of 0 or not, right? If you show me this and the computer takes 3 sticks, you can just say computer wins. That's fine. All right, and then I'll do that again, and I'll you know, let the computer go first, and I'll play randomly, and the computer should win. And I'll do that again, and I'll let the computer go first, but I'll win. So I'll bring it down to where I win, and I'll make sure that it understands that. All right, and so I'll play the game a few times, and then I'll check the error handling. So I'll put in some illegal numbers here, and I'll make sure that it keeps asking me how many sticks to play with until I put in a legal number. And then it'll say who should go first, user or computer, and I'll put in some non-answers and make sure that it keeps asking me. And then I'll say, okay, user goes first. And then I'll see if the error handling on this works. So I'll make an illegal choice and then a good choice. And then I'll make another illegal choice and a good choice. And I'll make sure that it keeps asking me, you know, one time to change my answer. And then I'll put in 2 illegal choices in a row and make sure it exits the game at that point. And I'll do that a few times. So I'll you know, try some negative numbers, and I'll try some letters, and I'll try some numbers that are too big, and so on. Right? And that's pretty much what I'm going to do. And if it's working correctly for all of these cases, then I'll go ahead, I'll look at your code, I'll make sure you have a block of comments on the top, you're indenting, you've got comments on your statements and so on, and you're probably good for 100%.
The dialogue, does it have to, I mean, it should be pretty close to this, but it doesn't have to be exactly everything.
Doesn't have to be exactly this. You don't have to say good luck. You don't have to say welcome to my matchstick game. But, you know, some kind of introduction and ask the user how many sticks. Some kind of request for who should go first, lowercase u for user, c for computer. And then, you know, show the pile of stick. You don't have to do the initial pile. It's not actually in the assignment. But, you know, either take sticks if it's the computer's turn, or ask the user, show the new pile, and just keep going like that. Tell me how many sticks the computer's taking.
If the line for remaining pile and the sticks are right below that, is that a problem? Should it have to be on the same line?
Like remaining pile, colon, and then the sticks on the next line?
Yeah.
That's fine.
Okay.
Yes, you can ask the user to tip the computer for good service, definitely. So you can do this yourself on your code, right? And get a pretty good read for, you know, am I going to get 100% on this assignment or not? And you know, low-hanging fruit, make sure that it's in a subdirectory named PA1 and that it's called stick and that stick is executable. And make sure the basic gameplay works. And then the nuances are, you know, handling the error conditions, things like that. All right. Anything else on PA1?
Do we need the remaining pile comment, or can we just show the, it was your turn, I just took sticks, and now you just show that there's less sticks?
You can just show the number of sticks. You don't need to say remaining pile. That's fine.
getting creative with the error handling?
You can get creative with the error handling, just don't, delete all my files or something.
Right, well, I'm more like, the computer's gonna get bored with you.
Yeah.
Not saying U or C or something like that.
That's always good stuff.
So I ran across it by accident, I think, or I know I didn't run across it by accident. There was a locomotive that ran through my command.
Yeah. Did you figure out how?
I believe it was capital LS.
Yeah, when you want to see the files in your directory, you type ls. Well, two common typos are either accidentally having your caps lock on and typing uppercase ls, or switching the characters around and typing sl. And so either of those runs the sl command. Sl is short for steam locomotive, and so it gives you a picture of a train going across your screen. So that's just a nice little Unix command.
How is that done? Is that just like a snapshot of like, individual, like it's here, it's here, it's here, it's here, and then run over, like, just like kind of loop through all of those states of the picture.
Mm-hmm.
Basically.
So was that a question?
Yeah, that was my question. I was just verifying that that's how they're doing that.
Oh, they're really just outputting a bunch of stuff to the screen, but they're putting a little delay in it also. Actually, we're about to talk about I/O redirection, and we can use that to explore this command. So that's actually good timing. So let's talk about I/O. And this gets into a sort of bigger aspect of Unix. Normally when you type a command in Unix, like if you say date, what does it do? It shows me the date. If I say pwd, it shows me my current directory. If I say basic calculator, it lets me type something from my keyboard, and then it displays the results of that calculation on my display. And this is the usual thing that programs do, right? They wait for us to type something maybe, and they generate some output that we can see. But there's actually something else going on behind the scenes that's making this work the way that it's working. And this has to do with what we call input and output streams. And there's two main streams we want to talk about. One is called standard in, and the other is called standard out. And all things being equal, standard in is basically our keyboard, and standard out is basically our display. So keyboard, is the thing I'm typing on, right? It's that thing, right? And display is, this box that has characters that can appear in it. And so when I say ls, if there was, output to be produced, it would display it there. And then here's a prompt which is being displayed by the bash program, and so on and so forth. But when I say date, right, date does not actually have code inside which says, find what the person's terminal is, right? Find that this person is running a program called console, and let's display some green characters there that show the date. Okay, that's not what the code of this program does. What the code in this program does is says, let's figure out what the date is, let's change it into a bunch of characters, and let's send those characters to the stream called standard out. Now Linux and Bash have set things up so that anything that gets sent to standard out from anywhere will show up on my display. But that's just the default behavior. And we can change that behavior. We can actually change standard out to be, instead of my display, something like a file. And so the syntax for this is to type in a command like date, followed by a greater than sign, followed by the name of a file. So if I say something like date greater than, let me just call my file f, something very different happens. Suddenly, the date command doesn't appear to display anything. Well, it still did. Date did exactly what it did up here. It figured out what the date and time were, it turned it into a bunch of characters, and it sent those characters to standard out. But because I said greater than sign F, standard out was no longer connected to my display. Instead, standard out was sent into a file, in this case a file called F. And if I were to look at the contents of that file, it's got the results of the date command from when I ran it. So we can use this greater than file notion to capture the output of a command. And we can do this with pretty much any command we want. So if I say something like df, which shows me a list of all the files on my system right now, right? If I say df and I send that to a file called f2, nothing comes on my display, right? But now I have a new file called f2, and if I look at the contents of that, it's the result of the df command. So any command that I can run on Unix, I can potentially capture the output into a file. And then I can cat that file if I want. I could rename it, I could move it, I could delete it, right? It's just a file with a bunch of text in it. But that text is whatever the command that I ran generated. So, you know, if I have my talking cow saying this is fun, I can send that into a file called pic. And now I've got a file containing, you know, a bunch of characters that happen to look like a talking cow. But it's just a file. It's an 8-line file, 169 characters. Everybody get what this greater than sign is doing? So let's look at the SL command. SL is showing me a steam locomotive. So I could say SL and I could say greater than, and I could put the output of that command into a file. And I don't see anything on my display. And it took a little while because, you know, the steam locomotive takes a while to get across your screen. But it created a file called F. And it's a pretty big file. It's about 30,000 characters. So if I look at that file, it's got a bunch of stuff in there. This is the stuff that was produced by the SL command. And theoretically, if I were to display this on my display, I would see the steam locomotive. So I could cat F, but it's a really, really fast steam locomotive. Right? So the thing is, to display 30,000 characters on a modern system, it happens just like that. And when I cat this file, it actually is showing the train going across my screen, but it's happening too fast for me to see. So I can run it through the more command, which shows me a part of my file at a time, and lets me hit a space bar to show the next part of my file. And if I do that, I can sort of see my train moving slowly across. But it's a little goofy because while my train is moving, I'm also getting this message from the more command. But you can see that, like, you know, the contents of this file is the stuff that was needed to display a train moving across my screen. So the SL command not only sends that stuff to the output, but it puts a time delay in the generation of those characters so that you see, you know, the animation slowly. But since I just captured that and put it into a file, if I just cat that file, there's no time delay, so it just comes out really fast. All right, so another thing we can do is we can direct standard in. We can say command less than something, and we can make the command read instead of from our keyboard, we can make it read from a file. So if I say command, so when I say date greater than F, it basically takes standard out and instead of sending it to the display, it sends it to this file. If I say command less than F, or let's say F2, then the command, when it wants to read from standard in, instead of reading from the keyboard, it will read from this file F2. And out of ink. So we can redirect standard in and standard out. So for example, there's this basic calculator program, BC, and BC does two things. It reads from standard in, so I can type 2 plus 3, and then it calculates the value of that expression and displays it to standard out. So if I could make a file called in that contained, 2 plus 3 plus 4 plus 5, let's just do 1 plus 2 plus 3 plus 4 plus 5. Right, so here's my file in. If I say BC less than in, it'll run the basic calculator program, but instead of reading standard in from my keyboard, it will read it from this file, which means it will see this as the thing it's supposed to calculate, and it'll calculate that, come up with a 15, send that to standard out, and then exit. And if I say BC less than in greater than out, it doesn't appear to do anything, but in fact it created a file named out which had the output produced by BC. So we can adjust where the input comes from and where the output goes to. All right, there's a third stream, which is called standard error. And standard error by default also goes to your display. And this is used to display error messages. So for example, let's make a file bad.c. So if I try to compile this file, I should get some error messages, right? It doesn't know what haha is, and it was expecting an equal sign here, right? So if I do this compile and I send my output to a file called output, guess what happens? I still see these messages on my display. And this file called output is empty. So I said when you run a command, it reads from standard in, it writes to standard out. But a lot of commands will actually send errors, not to standard out, but to this third stream called standard error. And the greater than sign changes standard out to go to a file, but standard error is still going to the display. And that's a good thing, right? Because if I'm running a program and I'm capturing the output in a file, if something unexpected happens and that program needs to report an error, it would be better if it actually showed that on my display instead of just silently putting that error message in a file where I might not notice it. But if I want to actually capture the contents of standard error and standard out in a file, I can say command and I can say greater than ampersand, some output file. And that will cause both standard error and standard out to go into that file. So now if I do my GCC command, but I say greater than ampersand, nothing showed up on my display, and if I look at the output file, it's got my error messages in it. So mostly we work with standard in, standard out, but for example, if you're compiling your program and you're getting 5,000 error messages and you want to be able to look at those, you could send those error messages into a file by doing this greater than ampersand. And like everything in Bash, spacing matters, right? So if I put a space here, I get weird stuff. All right, questions about that?
Can you use the ampersand by itself, or it has to be with the greater than?
It's got to be with the greater than. If we just use an ampersand, that's something totally different, which we'll talk about. That's called running a process in the background. Part of what's weird about Bash is there's all these things that really don't make any sense, right? Why should this redirect standard error? And if I just, put an ampersand without a greater than, why should it run my process in the background? It doesn't really make a whole lot of sense. I don't think people were worried about it being, predictable when they were developing this. But I mean, it's kind of like, why does ls mean show me the files in my directory? All right, so let me leave you with talking about pipes. Yeah, ls stands for list. That's what I think, at least, too. But then there's like awk and grep and things like that, which mean something, but not necessarily very clear. All right, let me talk about pipes. So let me show you something that's potentially pretty useful, right? So here's the current date, and it sends the date to standard out. Okay, here's the cow say program, which if I don't tell it what I want the cow to say, I can type something in here, and it will read from standard in, and whatever it reads from standard in, that's what the cow will say. I could put those together. Acquire text from string. I like that. I can put those together. So I can say, let's take the date, and let's send the result of the date command to an output file. And now let's run cowsay, and let's read standard in from that same file. Guess what? I've got a cow that tells me what the current date is. And this is something we're going to do a lot, right? We're going to constantly want to take the output of one command and read that into another command. And if we can do that, we can do a lot of things in Unix, in Bash, that we might not normally be able to do. For example, there's a program called word count, which tells me how many lines of input it's read. And there's the ls command, which shows me a list of files. Well, if I take the list of files and I feed that to word count, that'll tell me how many files I have in my directory. And there's going to be a lot of cases in this course where we want to take two commands and sort of put them together, or three commands, or five commands. Take the output of this and use that for the input of the next. Take the output of the next, use that for the input of a third, right? And there's a way to do that in Unix, and this is something called a pipe. And it's very easy to use. Type the first command, type a pipe, type the second command, and bingo, the output of the first command is used as the input for the second command.
Starting to sound like functions.
Yeah. And this is where Unix gets really fun, right? So if I take the date, it gives me all of this stuff. If I just want to know what the day of the week is, I can use a program called awk, and we'll learn how to use awk later. But if I say awk, quote, curly bracket, print $1, it'll print the first word of this line, which is just Wednesday. And if I take that and I pipe it into cowsay, now my cow tells me what the day of the week is. And without pipes, we can't really do this, right? There's no cowsay version that says, show me a cow telling me what day of the week it is. I don't need there to be, right? I can just say, show me the date, and do this cryptic looking thing to pull off the first field, which is the day of the week, and then put that into the cowsay program. So we're going to use pipes all the time, and pipes are one of the main things that makes Unix so powerful, is the ability to put these things together like this. And so it means we're going to learn a small set of commands, and we'll just get creative in how we put them together. All right, send me an attendance note, please. Let me know you're here, and we'll call this good for today. So we'll play around with some other things related to pipes tomorrow, and we'll work our way up to functions, and then Friday we'll start talking about PA2. All right, so I'll see you next time.